Now I want to talk about the IODA subsystem. So the JEDI system, this is a picture that Yannick showed earlier this morning, that has all this common functionality and code that's kind of in the middle of this diagram. And then on the left side, you have all these models that can get attached to the system. And over on the right side, you have all these observation types that come, measurements from instruments that can be attached to the system. And the whole idea behind this is that you've got a particular model and you can attach it to the system and you instantly get access to all the other stuff in this diagram just by attaching your model, and you can save yourself a lot of time because you don't have to develop all these OBS operators and interfaces to different OBS, values and things like that. So one of the key things that JEDI provides is this really high leverage of work that's been done already. So as I was saying, you add a model and then you just have instant access to OBS data, forward operators, DA flows, and all these things that have already been developed, and you can just take off and go at that point. The IODA stands for the Interface for Observation Data Access. And what it can be kind of thought of as operating on three levels. One level would be a long-term storage, like an archive type of system, and we have an archive system under development now that's called R2D2. And then you pull a particular cycle or time period out of this archive, and you put those files on disk, and those are getting prepared to run through a 1DA cycle. And then you read those files in and you have all the observations in memory and giving it access to the UFO and the OOPS system. And that's the in-memory handling. So you have this kind of archive and then files for immediate access and then memory for the systems during the run levels. And there are kind of two primary environments that we're targeting this for. One of them is for plotting and analyzing and going through diagnostics and stuff on a workstation or a personal laptop and things like that. And the other one is to be more of like an operational mode where you're running DA flows on HPC systems, many MPI tasks, threads, GPUs, things like that, and running big problems through in an operational mode. And the primary, one of the primary objectives or goals of the IODA system is to get this separation of concerns so that you can isolate the work of the science from the means of how the data is being stored. So the engineers can focus on optimizing the data storage and getting that all to work efficiently, and the scientists can focus on the science that they're trying to develop and publish in that. So you get this nice separation of concerns. We went through an exercise roughly 2 years ago to collect a bunch of requirements, and I just kind of wanted to mention this on this slide here, that we are being driven by requirements that are coming from customer or from users, and these things pertain to flexibility and access, good access to data and the metadata that describes these data. Having efficient, fast I/O, efficient compression, so it's not taking up gobs and gobs of resources, hardware resources. It's portable. There's a way to provide security for data that isn't publicly or isn't to be available to the public. It'll support the analysis flows. We can do data import from many different kinds of file types like buffer and grib and netcdf and metars and so forth. Easy to use, try to have a simple interface to that data from inside the system. Reliability, being able to sustain a run that's doing millions and millions of observations and not have it crash and things like that. And replicating existing functionality. So demonstration that it can handle operational, sized problems. Uh, this is a diagram that Yannick showed this morning. Basically, what we would like to do is replace all these different formats that kind of evolve through a system through a whole numerical weather prediction chain, and get it down to where there's one file format, one interface that goes into these different pieces. So you can pull in data from the GTS network, convert it once into this IODA format, and then at that point, the same IODA format and the interfaces are the same to go and pull data into a DA flow and then do pre-processing like thinning and super obbing and stuff like that before the flow. And then post flow, you can do the plots and diagnostics and monitoring during the flow, and it's all the same interface and file instead of having to convert between all these different pieces. So we can dive into the IODA system and take a look kind of at the architecture level. So we recently had a release. It was on June 11th, and we introduced IODA version 2, which has a structure like the green pieces here, and this is what was included in the release. So we've based the data model, which is this middle layer called IODA engines, off of the HDF data model. So that includes these things called groups and variables and dimensions and attributes, and a pretty rich data typing system. And I'll explain a little bit more of how these pieces in the data model work in the next few slides. And then up at the top is the storage implementation. Right now we're supporting this thing we call ObStore, which is an in-memory storage mechanism. And then HDF5, which is a file system that a lot of people are familiar with. It's the basis of what NetCDF4 is built on. And then down at this client-facing classes, the bottom part of this is what the client sees within the JEDI system. So right now we've converted our OBSpace and our bias classes in the JEDI system to be based on this IODA engines data model. And then there's more to come. One nice thing about organizing things like this is the implementation of the storage here up at the top is encapsulated from the API that's down at the bottom. So these pieces down at the bottom that are using this IODA v2 system see everything as this data model with these groups, varies, and dimensions, and it doesn't matter how it's actually implemented underneath, and that frees us up to optimize that part of the system. And the clients see a consistent, stable API, and it helps with this separation of concerns between the science and the storage implementation. So what's heavily under development right now, and it's going to be available over the next couple of months, are shown here in yellow. We've got active development of being able to have support for buffer and ODC. ODC is a library that gives us access to the ODB format that the Met Office uses. So that's for ODB files. And then we're going to be converting some of the internal classes in JEDI for diagnostics purposes. And then we have these converters that handle taking all the data from the providers in the different formats they have and converting it to the IODA format. We're going to have the converters be based on this model as well. And that's all active development right now. And then kind of in the future planning and potential, we could eventually use YAML as a source for data. And the purpose behind using a YAML would be, say you want to run a one observation DA flow so you can see the impact that the algorithms and things have on that single observation. Well, it's kind of a pain to write a file with just one observation in it. So it'd be really nice to be able to go into YAML and just say, here's all the observation data and the metadata and everything, and just read it in, and it builds the OBSpace that you can use to operate with that. So that's kind of the purpose of having YAML. And then maybe the direct NetCDF interface, because that might actually have better performance characteristics than the HDF5, and we might want to do a comparison at some point. And then we have more classes and containers that are inside the JEDI system that would benefit from being ported over to this system. So this is kind of the architecture and the picture of what's to come soon in the future. So to get into the data model layer of the IODA system, groups and variables and attributes are kind of the meat of the system. And the organization is an awful lot like a file system, where groups are analogous to directories. A group can contain another group, and you can build up a hierarchical structure that way, just like you can with directories in the file system. And then variables are kind of analogous to the files that live inside the directory. So groups can contain variables, and you can organize your data in that manner then in kind of this hierarchical structure like a file system. Groups and variables can also have attributes tagged on them, which is a very nice feature of HDF5, where you can put descriptive data such as like the units on a variable in an attribute, and keep important information kind of tagged along, with the whole data structure. So as an example, if you can have the blue boxes here are the groups, and then the green ones are the variables, you can build this hierarchical structure, and you can actually access the variables with a path that's like a path in a directory in a file system. So like this v1 variable can be accessed from the top by a/b/v1, like it's marked here. And in the same fashion, this v2 can be a/c/d/v2. So a little more information about attributes and variables. They can support a lot of different data types, like integer, float, string, and so forth. And they support dimensionality, which means you can view these things as being a vector, like a one-dimensional list of things, or you can view them as like a 2D array or a 3D array, and so forth. So in the case of the attributes, you can have a name of an attribute, you can have a scalar value like the string example here for the station ID, or you could have a 1D vector like this valid range attribute, goes from 0 to 100. Or you can have your own customized attribute that has 2 rows and 3 columns. That's this dimensionality or shape specification. And it gets organized as shown here with the values 1 through 6 in it. And so in an attribute, you specify the dimensionality by specifying a shape to the data, and then you load it in. So the difference with a variable is pretty much how you specify this dimensionality. With a variable, you still have that same rich set of data types supported, and I wanted to use an example here that kind of explains how the dimensions work on a variable. So if you think of the variable as maybe like a field that's a two-dimensional, like this grid that's up in the upper right, you got an x-axis and a y-axis, and the values on these axes goes from -5 to +5. So there's 11 tick marks in each direction. So what you do in this IODA model is you define 2 variables called x and y. You make them 11, you make them vectors and they're size 11, and you put the values, the coordinate values on the tick marks in here. So you have -4, -5, -4, and then through 5 for both the x and the y axes here. And then you mark these things as being dimensions, and the terminology that's used is they're called dimension scales. And then when you define the variable that you're interested in, you declare it as a two-dimensional variable, and you attach these dimension scales to it to define its dimensionality. So instead of just describing its shape, what you do is say that the X is the first dimension and Y is the second dimension. And the system will go down and look into the X and Y, and that's how it determines what its shape is, by seeing what the sizes of X and Y are. And the system has this ability to, if you decide that you need to make this bigger, you can change the X and the Y shapes, put the extra coordinates in, and get you can resize it and then put the new data in and stuff like that. So that's very convenient. There's also in a variable, this doesn't work on an attribute, but it works on the variables. You have this selection feature where you can take subsets out of the variable. And this example here is illustrating how you can take the middle 4 elements out of the variable that's actually 8 in length. And you tell it a starting index, and the indices start with 0. So 0, 1, 2 is this 3 is in the index 2 position, and then you give it a count how many pieces to take. And this is called a hyperslab style selection in HDF terminology. So we've got that same terminology here. And this is a way that you can pull out subsets of data out of a variable and do things that are more efficient than pulling it out and then taking these things, in your own code and everything. You can just have the system do it. So one more class that we've added to these HDF5 looking models is this thing called an OBS group class. And the OBS group helps with the construction and the management of a consistent group hierarchy that we're going to put observation data into. So, and it also comes with this thing called a data layout policy that helps make the view into it look consistent no matter how you implement underneath. So over on the left side is how the client sees the organization of the data that's in the data model. You have this OBS group feature that points to the top level, and then one level down you have a group called OBS value and another group called OBS error. And then each one of these groups contains a variable called T. So this OBS value is going to hold the measurement values that came from the data provider. And this OBS error is going to hold the estimates of the error that is associated with those measurements. And T is temperature in this case. And then you would access these by OBS value /T and OBS error /T. And you could implement this. Over on the right are 2 different implementations that show how you could actually store things in say like a file or something. You could have everything be in a flat representation where you just use the name with pieces that show the variable and the group name, or you could have it in a more of hierarchical structure where you have like we have our initial observations and then we thinned them out or something and have these derived observations. But then you always access it like it's the way on the right, and you don't have to keep adjusting every time we decide that we want to change the way this stuff is organized in the file or whatever. You don't have to keep changing how you access it in your code. And this just helps with the stability of the interface. So I wanted to kind of switch over and show how this all fits into the JEDI system at this point. So we've spent a bunch of time kind of describing IODA by itself, but now this is switching over to how it fits into the system. So we have 2 examples of minimization techniques, DA techniques. One of them is the variational minimization, another one's a Kalman filter, and there's these pieces that represent things that look like observations and observation vectors. And these are the Y0 and the H of X type elements, where the H of X is the simulated observations that you get from model information. And these all look like a string of observation values or a vector of observations. And then an observation space is just a collection of these observation vectors. So you make an observation space for radiosonde, another one for AMSU-A, and you put the vector of the values into each one of those and kind of keep things organized that way. And IODA is this implementation of an obs space and an obs vector that's part of this interface layer that's in the abstraction of the OOPS system that Yannick mentioned this morning. And in this abstract templated classes that OOPS provides, IODA is providing concrete classes that sit underneath these interfaces. So the obs vector holds the y and the h of x type values, and then the obs space is kind of like a collection of vectors, like a mathematical space. And it's based on this IODA obs group class that I just showed. And it provides access to obs data via the IODA data model and the API. So in a picture format, it looks like this. You have this templated obs vector class up in OOPS, and below the dash line is the IODA, the concrete IODA obs vector. It holds the data values in a member called values, and it has a pointer called obsdb that points to the obs space that it belongs to, that it's associated with. And then you have this plural obs spaces interface class that has a list of, in the spaces data member, has a list of singular obs space interface classes. And the first obs space might be radiosonde, and the next one might be aircraft, and the next one might be AMSUA, but it separates the obs spaces by the obs type. And then you have an obs space that lives underneath in IODA implementation with the actual data, pointing to the actual data. So one thing that the system does is the total observation vector is chopped up into pieces according to observation type. And the reason behind that is that the obs operators that are in UFO that need to run and create the simulation of those observations from the models, or the h of x values, those are different algorithms for, say, like a radiosonde and radiance and an AOD, like an aerosol optical depth. And this is a way of organizing things so that you pair up obs operators and obs spaces together, and they just know how to operate on each other, and they don't have to go through this big long list of if statements, figuring out what it is and that. So OOPS kind of sits on the tops and manages all these pieces with collectors that hold these objects in lists or whatever, and it manages piecing all the pieces together, running it through the cost function minimization step, and then putting the pieces back into the system with like the h of x values and that, so you can do diagnostics later. So this is a picture of kind of what that looks like. There's this thing up at the top, the observer, which is the thing that takes the model information, the model state X, and runs the obs operators on it. And these are lists of different types of obs operators. So they go through and do their own thing. They create an h of x value that gets stored in the obs space, and you can create an obs vector out of the h of x and send that on to the OOPS system and the DA algorithm, and you can get another set of obs vectors that are original observations, or the y vector, and then the OOPS system can make a departure, which is y minus x, and then go through the DA algorithm. And then also these obs spaces can write out to a disk to save data for diagnostics later. So I wanted to portray a schematic view of IODA at this point. So this is how we organize the data within. This is a different way of looking at the data model that I presented just slides earlier in this talk. It's more of an abstract view of how these groups and variables can be thought of. So you can kind of see how we're organizing and trying to make all these different kinds of observation types fit into one kind of like schematic view, which is here. So this is an abstraction, and it's not necessarily the actual storage structure, But you can think of these things as tables, where you've got this table in the middle that one of the axes are the locations, the position of where the measurement was taken, for instance, and the other axes are the different variables that you're processing. So in the case of like a radiosonde, you might have T, U, V, and Q as your variables. For Q is the moisture, and UV are the winds, and T is the temperature. And you have these latitude, longitudes, and heights and date times that describe what each particular location is. So in this table, this could be the actual observation measurements themselves. So they're analogous to this group that we have called obs value. And then each column is a variable that's underneath that group. So the columns are kind of analogous to the variables that are in the data model. So you can kind of see how that fits together. And you can have different tables where you have the error estimates and QC flags that come from the data providers, and then the results of H of X. And they all have T, U, V, and Q as their columns here. So these are, each one of these tables is like a different group. And then each column within the table is like a different variable. And then these are metadata that are over here. So you can make another table called metadata and make the variables latitude, longitude, height, and date time, and so forth, and organize it that way. So in the case of radiance, these you can have the different channels and that be stored within. So one of the features that we just added, I can see that this is an old system right now because we've kind of made the channels look like they're different variables, but actually there's just one variable called brightness temperature, and then there's another dimension that holds the channels. And with that, we can have another dimension of metadata that's indexed by the channel dimension, and have it store things like channel frequencies and channel wave numbers and things like that. And then we can put general attributes in. So you can kind of see the elements of the data model where we have groups, variables, and attributes and things in this schematic style of looking at things. And then we can also group different locations by station ID or ascent or flight and things like that. And I'll describe that a little more later on. So when we're reading observation data, there's actually a few operations that IODA will perform. So the first thing it does is time window filtering in between the DA window that you're working on. Say you're going to do like 1 6-hour analysis period. This would filter out all the observations that are outside that period, so that you only are operating on the observations that you need for the DA flow. And then we go through this grouping mechanism, which is the organization of locations into records. And this is an optional specification that you can put in YAML. And the purpose of grouping is to keep structures such as radiosonde sounding intact when you do MPI distribution. You don't split that up across different tasks. And then this last thing is MPI distribution, where you, according to different algorithms that we have, you split up the observations on different MPI tasks to try to make the problem more efficient. We have at this point, we've maintained compatibility with the IODA v1 API, which was a pretty simple API that had these getDB and putDB interfaces. And we'll see more of this later, where you give it, if you want to get something out of the ob space, you call this getDB function, and you give it the group name and the variable name, and then a place to put the values that come back. So in this case, it's doing metadata / latitude and putting the values into lats. And you can get the different, you can read off the different tables like the metadata or the obs value or the obs error or whatever, and read that. And then the putDB works kind of in the same way. You load up a vector with the values that you want to put into the ob space, and you call putDB with the group and the variable names. And what YODA v2 is offering a much richer API that supports a lot of data types, and it supports STL structures and even eigen objects. And it also it'll allow us to do a lot more efficient organization of the data and things like that. And these are features that are going to be made available over the next several months as the system is developed. So initialization of an ob space or reading in data can be done in two different ways. You can read from a file, or you can algorithmically generate data. And so using this variational cost function as an example, and focusing on the JO side, we can go through some YAML examples here. So in the last lecture, I showed this one where you're declaring observations, and you have these ob spaces in a list. And you've got aircraft and AMSUA, and then inside the AMSUA, you get a file that is holding the AMSUA data. And you can optionally describe an output file to put the h of x results into. And you tell it that you're going to simulate brightness temperature, and you want these particular channels to go into the assimilation. And this is a little more information on the grouping. Say you got a radio sonde, and you want to use the station ID as a way to group things into unique soundings. These groups stay intact during the distribution of observations across the MPI task. And we have so this is like a single radio sonde sounding or profile in this example. And you can also optionally put a marker on it that sorts these groups. So if you want to go like in the ascending order of the observation values, this is useful for things like filters that are based on gradients and so forth. So in the obs grouping, you use station ID as the group variable. So every location that has the same station ID is going to be put into one group. And then optionally, you can specify a sort variable in the order. So if you're doing descending order of air pressure, you're doing the ascending order of the sounding. So that's what this is specifying. And we have another localization technique that's used in LATKF applications. And we're creating a subset of observations based on proximity to a given location. And this example here shows this syntax in YAML that's a repeated block. So you can define with this ampersand a name for a set of keyword. It was a section of YAML, essentially. And then this wherever you refer to this local 2000, you're going to get these keywords substituted in. So it's being referred down here with the asterisk in front of it. So this is saying localization, and then nested underneath localization will be these four keyword pairs. And then you can repeat that. So this just helps you save some typing. The algorithmic initialization is done two different ways right now. You can do a list format on the right where you just copy everything directly out of the YAML. And right now, and on the left, you've got a random value where you give it ranges, and then it randomizes the 10. In this case, the number of observations is 10. It does 10 locations within those ranges that are given. So you can quickly throw together a small set of observations. And these examples right now are things that exist in the system, and it's for an h of x application that auto generates observation values. It'll essentially take the background values and perturb them with small distances away, and do it at these locations that are specified in here. And we're soon going to be adding a feature where you can just do the complete specification of the ob space in YAML and not rely on this h of x application. So got a couple more slides here. The YODA converters are scripts and programs that get data from the data providers into the IODA format. I just wanted to show that we're handling quite a few different types here. This list has grown a little bit since when this was created. And we also just kind of wanted to give a quick list of like all these observation types that we've got. And this is a little bit outdated too. I think there's 30 of them here, and we're probably more up in the 40 or 50 range by now. And in conclusion, IODA is currently handling 30 plus OBS types with tens of millions of observations being assimilated in a variety of testbed and experimental DA runs. So it's doing a good job, but it still needs optimization and everything to get up to operational quality. The goal of having a single observation handling interface, so maybe that schematic view that I was showing, and way at the very beginning too, across the whole NWP chain is progressing well. At this point, we seem to be handling all the different kinds of observation data types that can come in, and without any problem with this data model approach that we've got. And the development for this year is focused on adding many more observation types and also doing a lot of performance optimization.